Hi, everybody. Thank you, Gregory, for introduction. Thank you for coming. I think other people might easily join because we are distributed database, and it's easy to join new nodes, unlike in monolithic systems. So feel free to join, feel free to leave. YDB will survive. As already told, I work at YDB. I'm fond of software performance, and I'm really happy to talk with you today about YDB, TPC-C, and high-performance benchmarking. So welcome on board. First of all, I believe there are three kinds of developers here today in the, among audience. Some people are database developers, probably it's minority, but most of you are developers who extensively use databases. And some people don't have database, probably another kind of minority, but I'm sure they don't use databases, but that's a dream to have someday some database. So what do these people have in common, except bugs and features? I hope more features than bugs. Well, database benchmarks are the common topic between all these three categories of people, because it's obvious that as database developers, we have to benchmark our database to check performance. But if you are application developer, you must check requirements for your application, because you must understand if your database has enough performance. And if you don't have database, you will have to benchmark multiple databases to choose proper one. Today we are going to speak about performance and TPC-C, but I will start from a very gentle introduction to YDB. I will talk about our benchmarks evolution, and then we will focus on TPC-C, which is best OLTP benchmark ever. And finally, to conclude the talk, I will present results of benchmarks of TPC-C in particular to compare Postgres against distributed databases. So let's jump to YDB. It's easy to jump in. If you have other kind of databases, please feel free to jump YDB, not just now, but anytime soon. YDB is open source distributed SQL databases. It's a relational database. It's mainly OLTP, but OLAP is available for testing. We are kind of mature system. We have thousands of servers in our installations. And feel free to start our database on GitHub. We are strictly consistent, which is extremely important for application developers. It means that in CAP theorem, we choose consistency when partitioned. And we have serializable transactions by default. I think it's very important to use serializable transactions as much as possible, because it helps to avoid a very subtle bugs. And we want more features than bugs. We are a highly available system. We support multiple availability zones. Consider a simple example. You have 3 data centers, and you have a distributed database. One data center can be down for some reason, and also you can lose a rack with servers in another data center, and YDB will be still read-write available, which makes us a mission-critical databases. By architecture, by design, we have no downtime for maintenance. You can roll out a new version without any downtime. And as I already mentioned, it's not just OLTP. YDB is a platform. We have OLAP support available for testing. Besides that, we have YDB topic servers. In few words, it's Kafka replacement. And we have projects like Network Block Store available on GitHub. So you can build anything you want if you want to run monolithic databases, but scale storage. You can take Network Block Store and build your own solution. So let's move closer to our main topic. Let's speak about benchmarks evolution. First of all, what is database performance? There are two key aspects. Throughput. We would like to handle infinite number of requests per second. And latency. With latency, we would like to replay requests before being requested. But there is a hard physical problem with that. But we hope that guys will fix it and we will be able to reply before being requested. Performance is very important for you as application developers and for business because it's not just technical aspect of system. It's a very important economical aspect of your system because if you have a very efficient software, you spend less money to run the software, and it's extremely important for any business. Before going to the open source, we were focused on scalability and used custom benchmarks. Also, we performed performance tests on a special testing cluster. As all of you know, probably, there is no perfect benchmark. And production load is usually different from any kind of benchmark. So we used a special testing cluster. It's huge enough. It has 250 servers, more than 1,000 databases, and more than 500 terabytes of data. Our customers run their applications on this testing cluster to test their applications. Same time, they generate very production-like load, and we test YDB in real, almost like in the field. But after we became open source software, we started to focus on efficiency, not just scalability. And also, it became very important to compare YDB against other distributed databases. And we have chosen two most popular benchmarks, YCSB and TPC-C. But very quickly after starting to benchmark our database, we discovered that these benchmarks consume a lot of hardware client-side. And you need almost exactly the same amount of hardware to run the benchmark as you have to run your databases. And please recall, we have some installations with thousands of servers. It's impossible to have 1,000 servers more just to run the benchmark. It's a very important, benchmark's efficiency is very important in context of monolithic databases and distributed databases, because monolithic databases are limited by single server hardware, while distributed databases usually are not limited at all. Consider running benchmark to test a database with just 4 CPU cores. And now imagine benchmarking database with 5,000 CPU cores. There will be a dramatic difference in hardware consumption on client side by benchmark itself. So we expected that we would took benchmarks and will start to improve YDB. But instead we took YDB and started to improve benchmarks. So actually it makes YDB a benchmark of database benchmarks. Let's move closer to our topic and discuss YCSB benchmark as a kind of introduction. YCSB is a very popular key value benchmark. Originally, it has been created for NoSQL databases, but now it supports almost every existing database in our world. NewSQL, NoSQL, old monolithic databases, any kind. And everybody loves YCSB for its simplicity. You might ask, why we would ever test key value workloads? Because still a lot of people would like to use key database for key value store. Also, it's very easy to analyze results of simple key value benchmark. And we believe that you can do distributed transactions well if you can do key value well. So we started to use YCSB and very quickly spotted multiple bottlenecks using YCSB. After that, we decided to add YCSB to our CI to find performance regressions And it was a very good idea because YCSB from time to time helps us to find degradations before we roll out our release on a special testing cluster. But besides that, we discovered that YCSB on a client side consumes a lot of hardware resources, and it's done by design. Moreover, TPC-C has the same hardware consumption issues. So that is why, ladies and gentlemen, let me introduce TPC-C, world's best OLTP benchmark. It has been introduced in 1992. So imagine 1992. It's a year slightly after dinosaurs died, but before Apple, Tesla, SpaceX, Android, everything we use nowadays, even probably before normal version of Linux. But currently, all database vendors, not just YDB, but also CockroachDB, YDB, TIDB, consider TPC-C as the only objective comparison for evaluating OLTP performance. And it's really yet simple, but yet powerful benchmark. TPC-C simulates e-commerce organization. It has warehouses, and they trade some sort of goods. In simple words, you start the benchmark and specify number of warehouses. And each warehouse serves 10 districts. There is a special terminal in each district, and customers make orders and payments using this terminal. Also, from time to time, they have to check order status, and all the delivery goes through this terminal. And rarely in warehouse, you have to do inventorization. So most of transactions are new order and payment. You might ask me, why we have just 4% of deliveries? Well, they don't lose any of goods. They just batch delivery. So everything you buy goes to you, and it's like Amazon. Why TPC-C transactions are so good? They require serializable level of isolation, some sort of. They are multi-step transactions, which fits well your applications. And it's a write-intensive workload. As a key metric, benchmark uses number of new order transactions per minute, called TPMC. Probably the only well-known implementation of TPC-C is a part of Carnegie Mellon Benchbase. It's a benchmarking framework based on JDBC, developed at Carnegie Mellon under supervision of Andy Pavlo, who is a star in database world. The benchmarking framework is awesome. It's beautiful. It's very easy to add new benchmarks. You can extend it really rapidly with a new benchmark. Also, it's really easy to add new databases. And YDB, our friends, also use Benchbase fork to run TPC-C. And we decided to fork Benchbase, add YDB support, and then upstream the changes back. But unfortunately, in our case, we got into a lot of troubles with benchmark itself. First of all, data import is done via insert operation, which is kind of slow in comparison with faster operations like upsert, at least, because upsert is blind write, insert is read-write transaction under the hood, upsert is really faster. But there are also special import operations like bulk upsert, when you can use bulks and really rapidly move the data to the database. And we have terabytes of initial data, so we had to wait for hours to import initial data even before running the benchmarks. I'm a very impatient person, and it's tedious to wait hours until I can run the benchmark. So I decided to improve it and changed insert to bulk upsert. But nothing changed. It was still very, very slow. Benchmark consumed all the available CPU client-side. Here is an example of perf flame graph art. It's kind of nice picture. And what it actually shows that we have multi-threaded benchmark with a single lock. There are many threads, but the lock is the only one. Because import threads generate random strings. Remember, it's Java. They share the same Java util random object, which has in its implementation under the hood spin lock. So every import thread just spins instead of importing initial data. We had to change this to thread local random to fix the issue, and we were able to proceed with benchmark itself. But we got into another trouble. One terminal is emulated by one operating system thread. Our minimal setup includes 15,000 warehouses, which gives us 150,000 terminals and 150,000 operating system threads. As you know, it's almost impossible to run so many operating system threads in Linux. Maybe not just, I think it's completely impossible in practice. So you have probably to run multiple benchmarks on multiple servers, which is not so good. It's done because of sync and async programming differences. In old programming languages, it was very easy to write sync programs and complicated to write async programs. Of course, you have future promise module in Java, in C++. It's kind of nice. But still, there are some things which sort of complicated. Go is way better in this sense because they have Go routines. And in my opinion, Go routines are simple and efficient and much better than future promise module. And recent versions of Java provide Java virtual threads. It's Java's attempt to go. Pun here is intended. So we changed to virtual threads and immediately fall into another kind of trouble. Benchmark consumes too much RAM client-side. In our setup, we had to have 600 gigabytes of memory. It's not disk capacity, it's memory capacity, 600 gigabytes of memory. My first computer had less disk than this amount of memory, a way more less memory. And it's not megabytes, it's gigabytes. So let's sum up initial requirements to run the benchmark. To load a small YDB cluster consisting of 3 servers, 150,000 operating system threads, and 600 gigabytes of memory. And to test YDB, we had to use 5 servers to run the benchmark itself. And YDB cluster is 3 such servers. It's crazy. Now, consider if you want to change scalability properties of your database, if you want to change how database scales, and you would like to test database on a cluster of size 9, 15, 30, 60, 89 servers. I took these numbers from Cockroach and Yugabyte websites. They provide TPC-C results for these particular setups. And of course, if you test your database, you would like to test it against other databases like YDB against CockroachDB and YDB. We calculated that in Amazon Cloud, a single experiment would cost $10,000. And half of this money would go to run benchmark, not the database itself. Again, very crazy. And we decided to follow a path of minimum changes, but maximum benefit. So we switched to a newer Java version, started to use Java virtual threads. Now, one terminal is one virtual thread, not one operating system thread. And we started to aggregate transaction history instead of keeping all the results in memory. It helped us to reduce memory consumption from 40 megabytes per warehouse to 6 megabytes per warehouse. Also, now one CPU core is capable to run 1,000 warehouses. For our setup, it gives us 90 gigabytes of memory and just 15 CPU cores. Well, at least now you can run a benchmark on a single server, not 3 servers. But besides benefits, we got Deadlock for free as a bonus resource. Because Java virtual threads kind of silver bullet for Russian roulette. Deadlocks are well documented in Java documentation, but it's not obvious that you move your application from operating system threads to virtual threads. There are such unexpected caveats. In our particular example, we used C3P0 connection pool manager, and deadlock happened deeply inside library, not in our own code. Consider example. Number of sessions is limited, and some virtual threads hold session, and they for network I/O, so they perform some kind of database request. While they wait for I/O, they lose carrier thread. It's operating system thread which performs this virtual thread. But other virtual threads call some kind of stuff which to obtain session, and they block carrier thread. Now you end with all carrier threads blocked. You can't finish network I/O, and but you hold all the available sessions. So nice example of deadlock. Our fork is available on GitHub. Also, we plan to upstream all the changes back to Benchbase, and we have started this process. Now, let's look on the results of TPC-C, not just speak about implementation, but let's do some comparison. If you compare YDB against CockroachDB and YDB, what happens? Happens a very unexpected thing. Postgres appears. Everybody asks, where is Postgres? Why don't we compare our distributed database against Postgres? And they don't care much about comparison with other distributed databases. So this time we changed our habit of doing proper comparison of systems, of similar systems, and we compare Postgres against CockroachDB and YDB. And of course, we have to do another Benchbase fork for Postgres. It's also available on GitHub. It includes everything we discussed so far, plus Hikari connection pool manager because of deadlocking inside C3P0. Our setup is simple. We have just 3 servers. Servers are really hardware rich to have enough space for vertical scaling. Because, distributed databases scale well horizontally. And Postgres is considered to scale vertically well. So we give here to Postgres enough space to scale vertically. We have 128 CPU cores. We have 4 NVMe disks, a lot of memory, high-speed network between servers, huge pages, Ubuntu Linux. And our requirement for the database is simple. Database should survive a single server failure, and of course, not lose any data. That is why, in case of Postgres, we use 2 sync replicas. In case of Cockroach and YDB, we use replication factor 3. Of course, there are infinite number of Postgres configurations. You can spend all your time configuring Postgres and do nothing else to earn money for living. And we have explored many different configurations. Unfortunately, it's out of scope, but let me sum up our impression about different options and configurations. More information you can find in our YDB blog about fault-tolerant Postgres configurations, their caveats and benefits. Well, first of all, there are fault-intolerant Postgres configurations. It means no replication, no write-ahead lock, Well, in particular, I would say it means you don't value your data. But these setups are extremely performant, extremely efficient. But as soon as you add sync replication, it becomes a huge bottleneck and limits vertical scalability. So again, more information is available in our blog. At the end, there will be QR code on our blog. Let's look on results. Well, here, Postgres is slightly ahead of YDB. It achieves slightly more TPM-C. And YDB is ahead of CockroachDB with a more different delta. But let's look on next slide. It's latency. Someone might decide that Postgres is again ahead, but this time it would be better to not be ahead of others. It would be better, here Lua is better. Latency is awful. It's really terrible. It's within TPC-C requirements, but for many modern applications, multi-second latencies are really too much. And as you see, distributed databases have a way better latency while having a slightly less throughput. Let's have a look on new order latency in Postgres. It's kind of art here. It's not even. It's not steady all the way during the benchmark execution. And here you can see important fact about Postgres implementation. You see how checkpoints work in Postgres. As soon as you start writing checkpoint, there is a strong latency degradation. At the end of checkpoint, you have very nice latency. But what happens when you have a nice latency? You have to write one more checkpoint, and you have one more degradation. Also, I spoke a lot about scalability, and we decided to check if distributed databases scale well using TPC-C, or it's just a theory. Here we added more servers to YDB, and as you see, if we add 9, 18, 36 servers, we have higher throughput, and latency is the same. So it shows how distributed databases can scale just using commodity hardware. Let's sum up TPC-C results. Postgres wins, attaining just 5% more throughput than YDB. But at the same time, it exhibits significantly higher latency. YDB is 30% ahead of CockroachDB, and distributed databases can be very easily scaled just by adding more servers. It's time to conclude this talk. And what I would like to say, first of all, if you take open source benchmarks, be ready to improve benchmarks, not your system. Please, if you implement a new benchmark, implement it in a way that it doesn't consume as much hardware as system under the test. YCSB and TPC-C are great benchmarks. I strongly recommend using either one depending on your application. And unfortunately, sometimes Postgres is not enough, but there is a relief. Distributed databases shine even in clusters with 3 servers. So here is the QR code. I see that everybody scanned it already, so we can move on to the last slide. Please hit me up during the conference, during the breaks. Ask your questions. There is my Telegram, Twitter handle. I tweet a lot about distributed databases. Feel free to subscribe and discuss distributed systems. And feel free to leave your feedback. I would appreciate it. Will help me to make better talks next time. Thank you very much for your time and for your attention.
Actually, I just checked what's with QR code. We need to be logged in into the system in order for these QR codes to lead to the actual voting system. So if you see just the talk page, that means that you need to click login, use your browser help to automatically insert your login and password, and finally be able to vote for the talk. Let's go for the questions. Do you have questions right now? Oh, you do. Please, you're welcome.
Thank you. Thank you for the speech. It was very interesting. I was expecting to be less understandable for me, I would say. But it's great. So my question is about distribution. So the YDB is distributed database as well as Cockroach, etc. But question is, how distributed can it be? So how far can you put the servers? What are the requirements for latency, for example, or for reliability of network, etc.?
First of all, about number of servers. You can use thousands of servers. Usually, you use multi-data center setup because you want to be able to survive single data center failure. And latency between these network latency between these data centers strongly affects transaction latency because you have at least sync replication. Also, you have some round trips to perform distributed transaction. In our case, it's not a secret that most of Yandex data centers are located in kind of golden ring of Russia, and they are not so far between each other, but you can build geographically distributed database. And depending on your transactions, you might or might not get higher latency. For example, if you have distributed transaction, it will affect your transaction latencies. But if your transactions are not distributed, for example, you touch just one row, or you touch multiple rows in a single shard, in this case, there is optimization, and your transaction is not distributed, but it's still serializable. And your latency will depend only on latency between your client, your application, and data center. Usually, you put application near a data center, probably inside the same data center, so latency will be negligible.
Okay, thank you.
Thank you. So let me also ask a few questions as your host. By the way, it's quite interesting hosting dozens of conferences and doing hundreds of talks. I made this ability to conjure questions. So basically, I do not prepare them. I just listen to your talk, overall image on it. And after that, on the stage, I just click my internal button. OK, I want to ask him some interesting question. And question automatically comes to mind. So I don't know what my next question will be until the last second. And it's always a little bit of surprise, and I fear that one day I will click this button and question will not come, and I don't know what I will do. So let's check how this magic works. And I want to ask you, for example, benchmarking. You are benchmarking the speed, the throughput, how many requests can you handle per second, different requests. But this is not the only selling point of your database solution. It is distributed, and you sell not only that it is fast, But you also sell that it's fault tolerant. And for example, if one data center goes down, like it can recover in some reasonable time. So what do you think? What are other tests that we can apply to distributed databases? Can we test anything else other than speed? Like how these databases can recover from data center loss or from hard disk loss? How these bases can handle like split brain distributed situation? How they can recover from bad network conditions and other things which may be of interest to your clients. So what else can you possibly benchmark?
That's actually a very nice question. Thank you, Gregory, for asking this. Well, a very nice test is to take YDB, run TPC-C, but 2/3 of warehouses, and then shut down data center. And see if performance is reasonable, if we survive this failure. And actually, we do such experiments. They are very nice. Subscribe to our blog. We are going to provide maybe YouTube video, how we killing YDB softly and hardly also. And it's a nice experiment. Also, it's usually done in Yandex. There is such kind of training. It's not us who shut down data center, but it's Yandex engineers, I think network engineers, who shut down the whole data center, not just YDB subpart. And all services should survive. You should be able to use Yandex Taxi, to listen to music, to speak with Alisa. And I hope it's not a secret. YDB is everywhere else. When you speak to Alisa, you also touch YDB. So it makes all of you YDB users already. Just start using proper API. And proper API for YDB is our SDK, not Alisa. Also, it's very interesting to check correctness of database. We have Jepson. It's popular. It's widely known. And we use Jepson to test that our distributed transactions not just fast and reliable, but also correct, which is crucial for any reasonable database. So also there are many sorts of benchmarks, but I think we will be out of topic to discuss all of them. But if you have questions, just hit me up. I will try to answer with pleasure.
The name of our conference, Tech Internals Conference, implies that we can and will touch deep technical topics. So any other questions from you, please? Otherwise, I will use my tricks to summon questions, and some of them are not so easy to answer.
Hello, Evgeny. Thank you very much. That's amazing presentation from business perspective. So I'm from Nexus, and I'm responsible for infrastructure. The question is about your configuration. You talked about 200 servers and 500 terabytes data on them. So it means that it's about, let's call them 2 terabyte useful information per host. And you showed, for example, 63, 38 CPUs. Why it's so small capacity? What's happened if you'll try to add much more? Because for modern NVMe disk drives, it's nothing. So, for example, if we'll minimize number of hosts, but we'll maximize the capacity of each node. Thanks.
Thank you for your question. Let me open the proper slide with these numbers. So, do you mean this slide? It's possible to increase the amount of data, and in some installations, of course, we have more data per host. But it depends on cache capabilities, because if you have way more data than you have memory available, you simply can't put much data into the cache, and you have higher latencies. Here, it's kind of in between when we have enough data out of cache, but still we have enough cache to have proper latencies, because we have very tough requirements on latency, despite being distributed. We have many customers who would like to have sort of 50 milliseconds on 2 nines or even triple nines. And that is why we use such configuration.
Thank you. And if no one else, I will summon my next question. I do remember that 20 years ago, while working on the Redmin remote control software, which is written in C, C++, assembly, one of the test rigs that I offered mangled with network. So basically what I did some virtual infrastructure to test Redmin, and I use virtual network, fully programmatic, and I configured it for test, so it dropped or corrupted Ethernet packets, resulted in pure network condition. And I emulated some end-user setups and checked that software still works somehow. Modern databases, they are intended to be used in data centers with some contracts about response time, latency, like we do expect that between our data centers, latency will never exceed 50 milliseconds or 100 milliseconds or any other threshold. For end users, like that can be different. They can make requests from one coast to another coast with lots of network issues between them, and so on and so on. So, while testing databases, what do you think about the network quality? Should we also test edge cases where network is not ideal? Or should we expect that network is a granted hardware layer, and our database should work under these optimal conditions? What do you think about this?
Well, in my opinion, we could recall, I don't remember correct title, but it's famous stuff, like top pitfalls of distributed systems. I don't remember exact word, not pitfalls, but it's kind of synonymous, similar peculiarities or something like that.
Issues, troubles, there are lots of English words for that.
But they use some more sophisticated word. Maybe use
shortcomings.
No, unfortunately no. But the meaning is understandable. And network is kind of main pitfall, because you can't rely on network. You can't rely on delivering your data. Also, you can't rely on usually on order of events. And besides that, you can't rely on capacity of your network. So you must do your benchmarking for your critical applications. Keeping all the stuff in mind, you should try break your network and check what's happening.